Here's a graph of a function. We're asked to create the graph of its derivative. So if the function is called f of x, we have shorthand notation f prime of x to say that that's the derivative. Okay, and a derivative is a representation of all the instantaneous slopes, all those tangent slopes. You know, right here, if we were to draw a tangent slope at x equals 0, it should probably be a horizontal line, right? Because if it's going to touch just once, if it's going to be tangent, then it should look something like this, which looks to be a slope of 0. So over here in my graph of my derivative, I'm going to put a dot at 0, comma 0. And the reason is because at x equals 0, my slope is 0. And then let's pick out another point. Maybe this point right here. Maybe that's 1. That's 1 on the x-axis. Think about what the slope is at x equals 1. That slope, it might be rise 1, run 2. Maybe it's a slope of 1/2. So I'm going to put a dot at 1 on the x, 1/2 on the y. Okay. And then another slope, if I try to estimate what that slope is going to be, maybe that slope at x equals 2 is going to be a slope of 2. So I'm going to put a dot at y equals 2 over here. Okay, so what I'm doing is I'm graphing all the instantaneous slopes on the y-axis. Like at 0, comma 0, I estimated the slope was 0. Okay, at 0 on the x, I should say, I estimated the slope was 0. At 1 on the x, I guess maybe the slope is 1/2. Maybe it's a little bigger. Okay, at 2 on the x, I guess that the slope was 2. And then over here, let's pick another point. Let's go on the negative side of the x-axis. At -1, the slope, the tangent line, if I make a quick sketch of it, looks like this, right? So it's decreasing. So that's a negative slope. And if I was to put a number to it, down 1 to the right 1, down 1, it looks like it might be a -1. So at -1 on the x-axis, my slope is -1. So there's my dot. And then if I pick another one, you know, if I go to x equals -2, I've got a steeper slope, so it should be a little bit further down. So see how the dots are roughly making a line? That's the graph of the derivative. And again, to emphasize, the y-axis represents the slopes of this original function. I just made some estimations. So the graph of the derivative of this function is this over here. Okay? I know that's probably pretty weird, so let's do another one. Let me think here. How about, yeah, we're only doing graphs right now. So let's do this graph. Yeah, that should be fine. There's f of x. Let's graph its derivative. So if I'm going to graph the derivative, the y-axis is no longer the y-coordinates. It has nothing to do with the y-coordinates in this original function. The y-axis represents the slopes at that point on the x-axis. So like x equals 1 right here. We're going to put a dot at x equals 1 on our derivative. But where do we put the dot? Do we put it up here? Down here? We're going to find that out by figuring out the slope, because that's what a derivative is talking about, the instantaneous rate of change. So what's the instantaneous rate of change at x equals 1? It's a guess because we're just estimating from a graph, but it looks like it's rising 1, running to the right 1, rising 1, running to the right 1. So the slope of the tangent line appears to be 1. Now if I pick something a little bit closer to the closer to x equals 0, so like let's do x equals 1/2 right here. If I was to graph that slope, the instantaneous slope is steeper, right? So the y-coordinate maybe is going to be 2 on the derivative. If I was to estimate the slope of this tangent line right here, it's just a guess, but I know it's got to be steeper than 1, so I'm just going to guess 2 for a tangent line. Let's get a little bit closer. Let's think about like maybe 1/4. So this line, it should be a little bit steeper than that tangent line that I just drew, because right here the graph looks almost vertical, right? So we should have a y value that's a little higher because the slopes are even bigger. But the slopes keep getting smaller and smaller, right? Smaller, smaller slopes. We're getting closer to 0. So like here at x equals 2, just a rough sketch. There is the slope at x equals 1. The slope at x equals 2 is close, but it's leveled off a little bit. It's closer to a horizontal line, closer to 0, right? So if this slope was 1, then I have to have something smaller for the tangent line at x equals 2. And x equals 3, it's going to be even smaller. It's going to be even closer to 0. So this is a graph of the derivative of f of x over here. Okay, so maybe one more for good measure. I want to, looking at that textbook, some of them are kind of weird. Here, I'll make one up. So this is the original function. I don't know how you'd make that with a, can't do that with a polynomial probably, so. Okay, but that's our graph of our derivative. So let's split this up. These points are arbitrary, okay? X equals -1, I'm just putting them in. You can put, if you have a graph that's not labeled, you can just make some points, some coordinates of your own to estimate. So let's talk about x equals -2. When students first do this, they say, okay, -2 crosses 0. Boom, that's my graph of the derivative, right? But it's not, because remember, the y-axis isn't location. It isn't where this is on the y-axis. The y-axis are slopes. So what's the slope at x equals -2? How fast is this changing? It's a positive slope, right? Because as I read this from left to right, it's going up. So it should be somewhere up here for the y-axis. It should be positive. And if I had to put a number to it, I'd guess, I don't know, 3. Okay? It looks like it might be going up 3 to the right 1. Just a guess, though. So at -1, I picked this. I put -1 right here because look, if I was to draw a tangent line to the curve at x equals -1, that's going almost perfectly horizontal. So it looks like it's going to be at 0 down here, has a slope of 0. And then how about at x equals 0? The tangent line looks like this. It's decreasing as you read it from left to right. So that means the slope should be negative. So at 0 in the x, I should have something negative down here. And then maybe x equals 1. It looks like it's still negative, but it's slightly less negative. So at x equals 1, we're negative, but maybe that's -1/2 for this tangent line I just drew. The slope down 1 to the right 2 is my guess. It's not as steep as this slope is, right? And then when we get to like x equals 2, if I was to draw a tangent line, it's horizontal, right? So at x equals 2, I have a slope of 0. At x equals 3, it's a slope of 0. X equals 4, it's a slope of 0. X equals 5 is a slope of 0. And then all of a sudden, I start having more meaningful slopes again. At x equals 6, if I was to draw a tangent line right here, it's positive, and it's maybe up 3 to the right 1 again. So maybe it's a positive 3 up here. Okay, so remember, you use the same x-coordinates, but you graph the slopes at those x-coordinates. And just a few more to fill in the gaps between -2 and 1. The slopes are positive, right? But they're going down. They're getting closer and closer to horizontal, so it should be dots like this. And then when I get to x equals -1, the slopes have leveled off to be 0. And then to the right of -1, then I'm gone into negative territory for those slopes. And then here I've leveled off. And then all of a sudden the slopes jump right back up for my graph, positive slopes. So there's a rough sketch of the graph of the derivative. Remember, a derivative represents the slopes of the original function. So this is a sketch of all those instantaneous slopes.